Hey, this is Leach with Simpson Math, and in this video, I'm going to be talking about probabilities with two-way tables. Now, you might recall seeing two-way tables when you first learned about categorical variables, and they look like this, where we would have one variable and the second variable, and then we're looking at kind of their interaction. We're able to use this two-way table structure to answer probability questions. So they're not variables, but I might kind of refer to them as variables if I do imagine I'm putting them in air quotes. This is a bit of an academically sterile question because we have 100 marbles just to kind of help make our math be a little bit easier today. So we have 100 marbles in a bag. Each marble has two attributes, either color or pattern. You'll notice that the color options are purple, orange, or cyan, and then the pattern options are solid or stripe. All right. So then we're gonna look at the two-way table to see how this is structured. So this particular question, I've gone ahead and I'm given us the information. I see that there are 60 solid marbles, there are 40 striped. Me describing that would be what we would describe previously as a marginal distribution. So if I completely obliterated, not caring about color at all, I would just see the 60 solid, 40 striped. That's marginal distribution back when we talked about just categorical variables. Well, today we can talk about a marginal probability. That's a probability that uses only the values in the margin. So the thing about the margins of like your pages, the margins of your screen or margins of your pages, the edges. So these edges here. But instead of it being a distribution, whereas the distribution was saying something, I think I might have it mentioned down lower. No, I don't. The distribution in this particular example would be just the fact that there were 60 solids and 40 stripes. Or in terms of color, the fact that there are 45 purple, 20 orange, and 35 cyan. That is the marginal distribution. The probability is just when you're looking at kind of a specific thing. So for example, the probability of purple, well, how many purple are there? 45 out of how many total? 100. So the idea is if I was to select a marble at random, what's the probability that it's purple? There's going to be a 0.45 or 45% chance that it's purple. What's the probability I select a marble at random and I get a stripe? Well, notice there are 40 that are attributed to being striped. 40 out of 100 would be a 40% chance of getting a stripe. Now there's joint probabilities. So joint probability is when two events occur together, and this is an and situation. So for example, I'm going to select one marble from the bag, one marble at random. What's the probability that it is both purple and stripe? So if I take a look back at my two-way table, both purple and striped, I'm kind of imagining their overlap here, and to see where their overlap is this 26. So there are 26 out of the 100 marbles in this bag that are both purple and striped. And we always have to be careful about the wording, because later we're going to be mixing things, and sometimes it might be an or maybe a conditional, but it's here that it's clear that I'm talking about one that says purple and striped, but that it has both these attributes. It's not, there's no other kind of condition that's stuck on it, and it's out of all the marbles in the bag as well. So there's 26 out of those 100s, or 0.26. Something I want you just to note and then kind of file away is that I know last time, or in a previous video, we talked about this and situations, and ands we typically multiply things, right? Because it's going to make the probability smaller. Notice that this 26% is smaller than both of these numbers. But if I multiply both of those numbers together, I don't get 26. That's interesting. File that away. We'll come back to that in a bit. So just a counter example, we're going to find the probability of cyan, a solid, and then cyan and solid. So we come back up to my two-way table. So probability of cyan, again, I don't care about any of the pattern attributes, just the cyan, so 35 out of 100 or 35%. The probability that it's solid is the 60 out of 100 or 0.6. And then the and is then this 21 out of 100. So this 21 is where it's both cyan and solid. So 21 out of 100. So it's out of all the marbles in the bag. And this is a little bit interesting. I say, This time, if I take cyan, the probability of cyan and probability of solid, 35%, and I multiply it by the 60%, I do get 0.21. There's a reason for that, and in a little bit, I need to cover some ground first. We'll come back to this, I promise. All right, so we'll file that away. Now let's talk about OR situations. So with OR here, just in general, think back to what I've talked about previously, where we just add up all of our disjoint outcomes or add up all of our disjoint probabilities. So, all right, we could just do that. This is my preferred method. So take a look at this question. So I'm going to select a marble at random. What's the probability that it is orange or striped? Or striped. So there's this children's book. It's called Are You My Mama or Are You My Mommy? I think it's Are You My Mama. There's a little duckling that trots around a farm or this wildlife place and goes upon from one animal to the next, just going, "Are you my mama? Are you my mama?" And then the horse says no, the dog says no, and then eventually on the last page, the mama duck says yeah. So this is that idea. What I'm going to do is I'm looking for orange or striped. So I'm going to go through my two-way table that I've just copied and pasted here. You can see the work is already done. But I'm going to ask each of these cells, each of these 6 cells, I'm kind of ignoring the totals right now. So I'm looking at each of the 6 cells, are you orange or striped? So it's the are you my mama? Are you orange or striped? So this first one, this 19, are you orange or striped? As you can see, I've said, no, you're not. Because it is purple and solid, which is neither orange or striped. All right, what about this one? Yeah, this one is orange or striped. It satisfies the orange. Now, let me go ahead and keep going for a second. I'll pause and do that. What about the cyan and solid? Nope. Purple or striped? Yeah, I accidentally put an X. Yeah, it is because it is striped. Now let's talk about this. Now it is 0, which is interesting. But with this 0 here, this is an and. Would I include it if this wasn't a 0? Would I add those 2 numbers? Yes. So this is both orange and stripe. So this is still an OR. I'm going to remind you about OR versus and. I might have done this in a previous video. If I have, skip ahead a bit. So when I order hamburgers from a restaurant, I like mustard and ketchup on my burgers. So if I order mustard and ketchup, I expect to see both mustard and ketchup. Please, no mayo, and I don't want it dry. But what if I'm feeling a little persnickety that day and I say, oh, I want it to be mustard or ketchup? Well, if it comes back just mustard, that's cool. If it comes back just ketchup, that's fine. If it comes back with both mustard and ketchup, that is also okay. The logical definition of OR is as long as I have at least one of the things I'm wanting that satisfies the OR. If I wanted to say, oh, I want mustard or ketchup, but not both, that would be what we call the exclusive OR in programming. It's often coded as that XOR, the exclusive OR, that is this or that, but not both. Your English professors might say otherwise. They might say that OR has an implied, but not both, but that is not the logical definition of OR. So the logical definition of OR, as long as we have at least one success or more successes, then that passes. So here this is orange and stripe, which satisfies both, so even better, yay. And then lastly, this cyan, of course, is. So just to recap, I'm just going through and being like, are you my mommy? No. Are you my mommy? Yes. Are you my mommy? No. Are you my mommy? Yes. 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 So we see that there are these 4 cells satisfy the orange or stripe condition. So let's just add those up. So orange or stripe, well, my numerator is my number of successes over my denominator, my number of total things out of 100. So 20 plus 26 plus 0 plus 14, there's my numerator. So that ends up being 60 out of a coincidence. So 60 out of 100 is that 60%, right? Something interesting here is that, let me get rid of these spell check thing. Something interesting here is that if I did take the probability of orange and I added it to the probability of stripe, I do get 0.6. I can just add them together. The reason for that, I'm going to kind of spoil it a little bit. My next question is not going to happen that way. In this case, I can do that because, do you see this overlap here? If I add up the probability of orange and I add up stripe, so really I'm adding 20 and 40. Notice I'm not then double adding this 0. I mean, I am, but it's 0, so it doesn't matter. So when orange and stripe are disjoint, okay, when orange and stripe are disjoint, we can just add them together, which was our addition rule previously for disjoint events. Notice orange and stripe are disjoint, so I can just add probability of orange to probability of stripe, and we get the probability of orange or stripe. We've already known this. That's because this is disjoint. Spoiling it a little bit, look at this next one. If I want purple or stripe, that's not disjoint. So notice, just going ahead and jumping to the answer here, notice it should be 59% when we add up our parts. But if I add 45 and 40, I get 85, which is not 0.59. Do notice that it's 0.26 bigger, because if I add purple, if I add this 45 and add this 40, I double add this center right here, double add this 26. So it gets added twice. That's why it's 0.26 bigger. Now, it's 0.26 bigger with this 26 because my total is 100. If it wasn't 100, it wouldn't be just like that, but it'd be whatever that percentage amount bigger. So let's backtrack for a second. And how would I like to do this if I'm working this question? Me, Mr. Leach, what would I do? Again, if I have a two-way table, I'm just going to play the Are You My Mommy? Are you purple or stripe? Yes. Are you purple or stripe? No, no, yes, yes, yes. So I add up these numbers, 19 plus 26 plus 0 plus 14. Obviously, we don't have to write the plus 0 because it's just 0. And then we get the 59. So we have 59%. But of course, if I add up purple or stripe, purple plus stripe, I don't get purple or stripe. That's because purple and stripe are not disjoint because we have that overlap. So again, this is my preferred method. If you have the option, if you're given a two-way table, or it's not too much trouble to draw the two-way table, do the two-way table. If I would use this formula that I'm about to write, or that I have on the screen. If it's maybe just a one-off question, maybe I don't have enough information to draw a two-way table, or it's just maybe not worth my time to draw the two-way table. If they give me just these three numbers, then probably. But often we'll have the two-way table. So this is the general addition rule. So this is used in or situations, regardless of the two events being disjoint or not. So if they're disjoint, it works. The addition rule that we did previously abides by this. But if the situations are not disjoint, this will also work. So here it is. It's a probability of A or B. Do what we just did before, the probability of A plus the probability of B, and then we subtract their overlap. So I don't have an example of me using this because I'm just going to do the two-way table if I get the option. But do take a look here. If I did 45.45 plus 0.4 and then minus 0.26, I would get this 59%. I would get the answer that I'm looking for. So this subtracts one of my overlaps that got double counted, so that way it's only occurring once. All right. So let's move on talking about conditional distributions. So recall a conditional distribution where we describe one variable in relation to a specific result of the other variable. It's a bit of a word salad. So just a reminder, if I want the conditional distribution of solid marbles, notice it would be like, oh, there's 19 purple, 19 purples that are solid, 20 oranges that are solid, and 21 cyans that are solid. So let me show you here. If I'm talking just about the solids, the stripes are dead to me. Even these totals are dead to me. And so I'm just like, oh, there are 60 total stripes, 60 total solids, 19 purple, 20 orange, 21 cyan. Or I could do it kind of relatively. So out of these 60 solids, I see that 19 of those 60 are purple. I can almost imagine a little ellipse, and I'm looking at these two. Or out of the solids, there are 20 that are orange, so 20 out of 60. Or again, out of the cyan, out of those 60, 21 of them are, sorry, I misspoke. Out of the solids, there are 60 solids and 21 of them are cyan. That's how we get that. So a conditional probability is just these things, but it's really just one of them. We don't have to mention the whole distribution, just one of them. So our conditional probability is this. It's the probability of B given A. This little vertical line here is a given. So I'm kind of pointing to this thing as a given statement. So this is B given A. So let me go ahead and spoil this for a second. I'm going to come back to the math here. To our English ears, that sounds a bit backwards. We'd like to hear the conditional statement like, oh, look at the sky. Given the fact that it's cloudy like it is today, what's the likelihood of rain? Or look at the sky. Given the fact that there's not a cloud in the sky, what's the likelihood of rain? You can base your opinion on whether you think it's going to rain or not by looking at the sky. Given that information, what's your opinion? So to our English ears, we'd like to hear the conditions first, but in math, we kind of do it, we do it the other way, so it kind of feels a little bit backwards. So just recall from your algebra days, if this is over your head, don't stress. But for some of us who might remember our algebra courses, then this should be helpful. So recall if I did domain in algebra, we might say it's the domain of some particular set. Don't worry, I'm not giving you the function or anything like that. I'm not giving you that information. Just what if I had some function, and the domain of that function is the set of x's, and we would usually in math world read that as such that. But in stat world, we often do given, but it's the same thing. So, oh, what's my domain? Oh, my domain is a set of x's. Oh, given that, blah, 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 blah. Given that my x's are real, my x's are bigger than or equal to 0. Oh, but x can't be 1. So given these conditions, the x's are my domain. So we do that because so we can just list out our conditions and not worry about these things. We write what we want first, and then we list out the conditions. That's how math works. That's the same way that we're going to communicate in stats. Okay? So we find the probability of what we want first, given that, oh, here are my conditions. So we can do this one of two ways. Just a second ago, I did this using counts. So among the 60 solids, there are 19 purple. So using counts, there are 60 solids out of those 19 purple. So look at the verbiage here. I'm saying it's B given A. So this would be purple given solid. So I have the probability of solid in the denominator, or just the number of solids here. So the number of solids is that 60. And then the number of A's and B's. So the number of purples and solids would be that 19. You can do it as a probability. It works because notice if I had 19 over 100, which is the probability of A and B, and I put that over the probability of A, 60 over 100, every time you do this, those bottom denominators are going to reduce out to 1, and we'll be left with just the 19 over 60, which is what we have here when it just counts. So you can do it in the counts form or the probability form. We'll get the same thing. Now do notice that the conditional statement, the given statement, is not commutative. Remember the term commutative? 2 plus 3 is the same thing as 3 plus 2. Addition is commutative, but subtraction is not commutative. 2 minus 3 is not the same thing as 3 minus 2. One is a positive one, one's a negative one. So similarly here, if I flip these two, B given A, we often get different results. So this is saying, oh, what's the probability that A happens given the fact that B has already happened, okay? Or given the fact that you know about B or whatever. So let's take a look at an example using this. So here's this statement here. I don't have the situation written down. I kind of made a mess of this table. So what's the idea here is this is the probability of purple given stripe. So remember, the given is first, that's backwards to our English ears. So the given is second, that's backwards to our English ears. So the idea here is I had my bag of 100 marbles, I reached in, and imagine I've sorted them. I've sorted the marbles so that way I only have a bag of stripes. So given the fact that you're going to pull a stripe, you know you'll get a stripe. So I've kind of drawn here, if you look at my table, I've drawn this awkward looking sock-like bag that is containing my 40 striped marbles. So in this bag, and I put a little ribbon around it so you can tie it close. In this bag, we have 26 purples that are striped. None of these stripes are orange, and 14 of the stripes are cyan, for a total of 40. So this marble bag has 40 marbles in it, 26 are purple, 14 are cyan. What's the probability that I reach into this bag of stripes and pull out a purple? Well, I have 26 of them that are purple out of 40 total, so that's going to be 26 out of 40. A little bit of a tip. Do you see this vertical line, our given bar? It is notably vertical. If you're doing scratch work or you're doing work and communicating your work, draw it vertically. But what if I slightly made it slightly slanted, kind of like a division bar? Notice that the stripe goes in the denominator because it's kind of in a denominator-y position. This is more of a mnemonic way of remembering things. The stripe is in the denominator, and then the purple among those stripes are in the numerator. So it's our purples that satisfy the stripes out of our total stripes. Also, remember that this needs to be less than 1. So if you did 40 over 26, obviously that would be a bad idea because your number is going to be bigger than 1. But just remember that the spreadsheet say, what's my total? Well, you can kind of think of this as the denominator, so the stripe goes in the denominator. All right, so let's compare that to stripe given purple. So order does matter, so let's look at it the other way. So this is, I've gone through the marbles, the 100 marbles, and I've made a bag of just purples. All the other marbles that aren't purple, I throw them away. I throw them out the window. So now I just have a bag of 45 marbles. Okay? Inside of this bag, all of them are purple. I peek in, oh wow, that's a lot of purple marbles. 45 of them. But, oh, some of them are solid in appearance. Some of them are striped. Oh, it turns out there are 19 of these purple marbles that are solid and 26 of these purple marbles that are striped. So I want to find so what do I want? I want a stripe. So I have the probability of stripe. I put what I want first. Oh, given the fact that it's purple. So given the fact that it's purple, here's my bag right here. So I want striped, which is 26. Out of, again, you remember you can think of this kind of a little division thing here. So my denominator is the purple, which is that 45. All right. So notice that if I flip these, it goes from being kind of a horizontal relationship to then being a vertical relationship in my two-way table. It doesn't matter which way you draw the two-way table, but it does matter which way you do this. Make sure that that number is the number that is in the bottom. And then it's always going to be kind of you could kind of keep going with this. Do you see how from sake of drawing a bag, I didn't include my total because this is the 40 things, but if I kept going, it's in the same direction. Let me show you it this way. I just drew my bag here because I didn't want to include the 45 because it's not a part of it. But if I did keep going to try to basically say, here's my relationship, I'm looking at just this column, and it's this 26 out of 45. You're not going to have a bag here and your total be over there. That doesn't make any sense. All right, so new thing that uses this conditional statement. So our general multiplication rule, it's used in AND situations, regardless of the two events being independent or not. So previously we talked about the multiplication rule, we didn't have general, and it was just P of A times P of B, right? That was gone, it was just P of A times P of B. But it was but A and B had to be independent. Well, what if they're not independent? Pardon me. What if they're not independent? Well then, we have this adjustment that we do by multiplying not just by P of B, but by the probability of B given that A has happened. So one, this kind of makes sense as a little bit of a story from left to right. So what's the probability that A has happened? Cool, let me write that down. Oh, given the fact that A has happened, what's the probability that I get B? So now it's finding the probability that both of these things have happened. That's why this A is second, because it's given the fact that that has already happened, what's the probability we get B, working left to right to tell that story. Also, look where this came from. Do you see this? If I took this and I wanted to solve for the probability of A and B, what would I do? Well, if I had, let's say 3 equals x over 4, and I wanted to solve for x, I would multiply both sides by 4, right? And I would get 12 as x. All right. Well, I want to solve for this thing, so how about I multiply both sides by P of A, multiply both sides by P of A. I'm going to choose to put it in the front. P of A over P of A reduces to 1, so I now have the probability of A and B is equal to probability of A times the probability of B, given that A has happened. Gee, that sounds familiar. That sounds like what we just documented here. Okay, so that's where this formula comes from. It comes from us just multiplying, just solving for this A and B. All right, do note that again, because the commutative, sorry, I misspoke. The other C word, the conditional probability is not commutative. If I wanted to do A and B, again, it doesn't matter here. A and B is commutative. A and B, B and A, same thing. But if I knew that the B happened first, or I know what the probability of B is, then this is A given B. The idea is whatever's first is then the second slot is in that conditional spot. And that fulfills what we said here as well. All right, cool. So, recall we looked at something earlier that was broken, right? We said, well, if I do purple times stripe, or probability of purple times probability of stripe, 0.45 times 0.4, we don't get the 0.26 that we were expecting because, spoiler words, there's an independence issue. Okay? Remember, we did talk about independence. We said we can do P of A times P of B when they are when they are independent. Well, clearly these two things don't equal, so clearly purple and stripe are not independent, right? So let's follow our formula. So the probability of A and B is equal to the probability of A times the probability of B given that A has happened. Well, it's purple and stripe. So what's the probability that I get a purple and also stripe? So I'm going to do probability of purple times the probability of stripe given the fact that purple has already happened. So here's the math. Probability of purple is 45 over 100. I'm going to multiply it times this 26 over 45. So I'm doing this 26 over 45. So probability of stripe given purple. Notice what happens to my 45s. They reduce to 1, and I'm left with 26 over 100. This works even on this one. When they did equal, spoiler alert, it's because cyan and solid are independent. When I multiply them together, they equal. That's because our just multiplication rule says we can multiply them together when they are independent. But if they're not independent, we have to stick with that. We have to do this probability B given A business. So even if they're independent, we can follow this rule and it will still work out. So I could just do cyan times solid and it will work out. But we can also do it with this solid here. Let me come up here. So probability of cyan, that's this 35 over 100. Multiply it times solid given cyan. So this is given cyan, probability of solid, 21 over 35. These 35s reduce, and we're left with 21 over 100. Right? So in this case, we get that 21 over 100. Over here, we were also left with this 26 over 100 when we did that multiplication. Obviously, remember we got that 26 over 100 just because we have this two-way table. But what if I gave you a question and you didn't have this two-way table? I just told you these two numbers. You would need to then multiply them together, which we're going to see in a later video, a situation like that. All right. So we can multiply them together where this happens times the probability that the next thing happens given the first thing already did. All right. So let's now talk a little bit more about independent events. So we said that when it's independent, I could just multiply by P of A times P of B, or P of B times P of A. So that must mean that if these two things, if A and B are independent, that must mean that P of B must equal P of B given A, or that P of A would equal P of A given B. All right, if you look back at the, multiplication rule, when they're independent, this is gone. It's just P of B. So that must mean if it's independent, P of B is going to equal P of A. Let's write that down. So independent events, A and B are independent events when the probability of A equals the probability of A given B. Or, from the other perspective, probability B equals probability of B given A. So here's how I think of this. I think of a little story, a little situation. So imagine what I might say or do by myself. So, how might I talk by myself? If I, oh, I do talk to myself, trust me. But what kind of words do I say? What language do I say? So how do I speak? What do I say by myself? Does it equal what do I say given I'm with someone else? So let's say I'm talking to myself, I'm doing whatever, I'm doing something, maybe it's something even slightly embarrassing. My husband walks in the room, so I'm doing something. Does it equal does it change? Am I going to change what I'm doing the fact that my husband walks in the room? Hopefully not, okay? Because I'm independent. I'm going to do whatever I'm going to do, whether he's in the room or not. That's not a flippant thing. That's because we live honest lives, right? I don't keep things from him. So what do I say about myself equals what do I say or do given the fact that he's in the room? All right. But maybe what do I say about myself? Does it equal maybe if my boss is in the room? Maybe am I going to talk a little bit more properly or politely, or use my work voice a little bit more, or especially like if I'm on camera, I might say things, I might not say things that I might do otherwise, right? So there's some sort of relationship there. If you're religious, what do you say by yourself compared to what do you say if your pastor or clergy member is in the room, okay? Or your parents in the room, something like that. So if what you say by itself matches what you say given something else is there, then you are independent of them, okay? You're kind of those in respect to that thing, you're independent of them. But if it depends on the fact that they're in the room, how you're going to behave or act, then there's going to be a difference and they're going to not equal. So let's take a look at these two examples. So are cyan and solid independent? We already know this to be true because we saw the math work earlier that we could just do that multiplication and it works. But let's do our check. So this is the probability of A. Does it equal probability of A given the fact that B is also in the room? Do notice that in this, I kind of think that how the A's are both in the front, but when I do my multiplication, they do switch. That's because these two things don't equal each other. What this equals, this is probability of B equaling this, or probability of A equaling this second part. So when it's multiplication, these roles kind of do switch. That's because this B has happened, and then I'm talking about B happening. What's the probability that this A also happens? So it's kind of that same idea. So don't confuse those two things. That's why I think of this story. What do I say? What do I say by myself? And then what do I say given something else is there? So let's say I'm going to pick cyan to be by itself. You could pick solid, and I'm going to pick cyan. So what's the probability I get cyan? Well, that's 35 over 100. And I've drawn this big oval here. So I'm talking about this marginal probability, marginal distribution. So I'm going to draw an oval around that entire distribution there, this entire marginal distribution, and then be like, it's this 35 and this 100. Why do I do that? Well, because when you're doing this independence thing, they need to be parallel. So the probability of cyan given solid, I need to draw another big old oval, and it better be parallel. Not this way or this way, not diagonal. Okay, it must be parallel. So if it's, which that one fact has saved me a few times, because sometimes I know which way this goes, but sometimes even my marginal, I'll try to accidentally do weird or thinking it weird. So this really helps. So this is given the fact that it's solid. What does cyan say given the fact that solid is there? So given the fact that it's solid, it's this top row. What's the probability that it's cyan? 21 over 60. So now let's just simplify and check. 35 over 100 is 0.35. And then you can reduce 21 over 60 to get 0.35. And so that means that cyan and solid are independent. This equals precisely, not kind of almost, because like I said, this is an academically sterile question. I made it up. I made it up intentionally for this to be independent and to equal precisely. In the real world, sometimes this is close. Maybe this is 0.35, and as close as we could get, and it's like 0.343. That's as close as maybe we can get. It doesn't round to 0.35, but it's close. Later in the course, or in some other courses sometimes that you might study, the chi-square test for independence to be able to determine how close is close enough. All right, are purple and stripe independent? We already know the answer is no. I'm doing it the other perspective. I'm doing the pattern first just to show you that you can. So remember, so whatever you say first, what does it say given something else is there? So probability of stripe. So now I have this marginal distribution over here. I'm going to grab my marginal probability of this 40 over 100. Does it equal? Oh, I didn't talk about this. I literally wrote an equal with a question mark over it. That is a mathematical symbol to say, does this equal? I don't know. Here it was fine because they do equal each other, but I still had it because I'm like, does it equal? I don't know, until I determined that it does. So does it equal? I don't know. I don't know. So what's the probability of stripe? Given the fact purple exists, again, must be parallel oval. So here's all my purples. Orange, cyan, totals are dead to me. So then we have 26 over 45. So now let's compare. 40 over 100, that's 0.4. 26 over 45, well, I already know that 26, if I double 45, I went backwards. If I double 26, I'm bigger than 45, so I already know this is more than half. And if in fact it's 0.5777. So notice that these two things do not equal. So I equal question mark because I'm like, I don't know. Oh no, they don't. Right? So since they don't equal, purple and stripe are not independent. But cyan and solid are. How does this kind of make sense? Because sometimes it's a little confusing how some are and some aren't. So I'm not saying that this variable is independent of this. I'm saying just this attribute about just cyan and solid is independent, whereas purple and stripe are not. So specifically here, if I pull out a marble and don't show you, and I go, ooh, this marble's cyan, that doesn't give you any more information to help your estimate for whether it's solid go up or down. Okay, because the probability of solid is 60%. But let me do this. I did that backwards. I'm going to reach in and pull out a marble and go, ooh, this one's solid. This doesn't give you any more information one way or the other about it being cyan. Because so given the fact that it's solid, what's that probability that it's cyan? Well, 21 out of 30, 21 out of 60, or 35%. Well, given the fact that it's solid, I want to know, is it cyan? Is it cyan? Well, the probability of cyan is still 35%. My estimate didn't go up, didn't go down from it just being by itself. This information about it being solid isn't helpful. Versus, look at this stripe situation. I want to find out if this marble is striped. All right, I'm going to reach in this bag and pull out a marble and go, ooh, I'm not going to tell you about it being striped, but I will tell you that it's purple. You go, okay, well, given the fact that it's purple, there is a 57% chance that it's striped. Among all stripe, there's only a 40% chance. So my percent chance that it's striped has actually gone up. Me knowing that it's purple, there is a relationship between those two things. And lastly, just kind of as an analogy to help you kind of make sense of there being two things that are independent and something that's independent and something that's not. Think about being in band, like a high school band or your local city symphonic band or something. Broad strokes, typically, more females tend to play the lighter woodwind instrument. So let's look at the flute section. There's going to be usually a whole lot more female flautists than there are males. Just how it tends to be. Look at then the tubas. Broad strokes, there tends to be more males playing the tuba. Though when I was in high school band, my junior, senior year, the tuba section leader was a kickin' female. She was awesome. So, always there are exceptions to the rule, but she was the only female leading a whole bunch of men, or boys, or high school students. With that, there's clearly a relationship between gender and instruments. But if I was like, look at the saxophone section. The saxophone section, maybe trumpets, but especially like, let's say saxes, those tend to probably, maybe, there's a good chance that, let's say your band is maybe 60% females, 40% males, that your saxophone section might also be 60% females, 40% males. It will also have a similar breakdown to the gender breakdown as a whole in that. So we could have some parts that are independent, that do have or depend on gender, that there is a dependency or a non-independence of gender, and then some that aren't, as just a little practical application for making sense of this formula. All right, so in my next video, I'm going to be doing some just kind of rapid fire, going through a whole bunch of examples, applying all these things that I taught. Might be broken up in more videos. I don't know, I haven't done it yet. But so I hope this helped you understand doing probabilities for and, or, conditional statements, independent things in a two-way table situation. Hope it helped, and I'll see you in the next one. Bye.